Okay, people, let's talk about solute and solvent interactions and how we can look at different kinds of things, how they interact with water, and how things dissolve and some things don't. Okay, so a couple things to obviously point out. Okay, salt dissolves in water, but iodine does not. Neither does oil. Okay, why does iodine um, dissolve in alcohol, but salt does not? So we see all these different kinds of examples in the real world all the time. Okay, so this is an unfortunate oil spill where we see that oil is less dense and it's going to be on the surface of the ocean water. Here's our line right here. We see this with Italian salad dressing, where we have our vinegar on the bottom and we have our oil on top, and you always have to shake it in order to get both oil and vinegar out. And then we see fun little applications of this whole thing where we see these paperweights, and the paperweights are going to have your mineral oil, your baby oil on the top, and then basically a blue water on the bottom, and something with a density in between, a plastic dolphin or duck or frog or sailboat. And those are all examples of things that mix and that don't. So, how are we going to know if things mix and things don't? Well, it's through this very famous chemistry proverb, like dissolves like. Not a proverb, but it's pretty much seen as one of the most common things that we do know. Polar solutes will dissolve polar substances. Polar means that there is a partial positive and a partial negative end. So if it has a positive and a negative end, that means that they can attract one another and therefore pull it into solution. Hence our piranhas, which I now know how to spell, Piranhas. I didn't know how to spell it. I don't teach English, just chemistry. And like dissolves like also refers to nonpolar solutes dissolving nonpolar solutions. So water is polar. We know that it has oxygen and hydrogen. It has two lone pairs up at the top over here. So this is the partial negative. Here's the partial positive, like we talked about earlier in the year. This is the positive part in this polar bent molecule, bond angle 104.5 degrees, all that stuff that we know from around midterm time. So if water is polar, it will only dissolve polar things. So what's polar? That's going to be all of our ionic substances, acids that begin with H, and bases that end with OH. Okay? And oil is nonpolar. It is a covalent compound. Okay, there's going to see all of those nonmetals in there, and you will see that they will not dissolve. They will be immiscible. They will float or sink in water. So here again is our diagrams of our water molecules. We have our lone pairs. Come on, you want to get in there. Our lone pairs with our two electrons here, making this a partial negative. This is our partial positive, and we end up seeing that the dipole moment points up that way, and that negative charge allows for things to dissolve in water that are polar. Okay, so if you have a solid crystal, it basically surrounds the crystal. Water molecules, I say all the time, is like a pack of piranhas chipping away slowly but surely, and kind of surrounding, so you can have this maximum amount of solute to solvent, and that's why you have your solubility curves. And you can see them kind of all gather around, all the way around on each side, pulling them into solution. So this would be your aqueous saltwater solution in there. Okay, so what if you are soluble? How are you referred to? You are referred to as being miscible. That means that you can dissolve in your substances in water. Okay, Immiscible means that you cannot. Okay, so hexane in water is going to be a carbon hydrogen compound, and you're going to see that it is non-metal, polar and a non-metal compound, so it forms layers. We see our oil and our water over here forming layers, and we see that we have a really nice density column here. Yes, you can try this at home. This is Caro corn syrup, which has a really high density at the bottom. Here is your water, here is your oil, and obviously the cork is going to be the least dense. This Lego piece of plastic will float in between the oil and water. That's how they get all those really cool paperweights. I believe this is a grape. And then if you put something like a penny down here, you can get that to sink down at the bottom. So some ways that you can occupy your time with that. All right, so what is an application of this? Well, we can use paper chromatography, which some of you might have done in biology class. And that's where you basically are going to put in a beaker different kinds of solvents. And in class, we actually do a lab where we have 3 solvents. The first one is where we take a look at the effects of water. The second is going to be on rubbing alcohol, which is C2H5OH. And the third, which I don't know if you can see, is going to be your acetone, which looks like this. My pen isn't working right now. Which looks like this, where you have your methyl groups here, your oxygen, your methyl groups here. So these guys are both nonmetals, and this guy is going to be polar, and you can see what dissolves in it and what doesn't. So we basically take ink. I like to use secondary or tertiary colors. So you make some dots here at the bottom with your different color inks, and as the substance um, sits, the paper chromatography paper, which is basically like filter paper or coffee filter or something like that, sits in the solution, the solvent will start to move, and it will gather up and pool the different parts that make that actual shade or color um, with it. Okay, the big molecules will be down at the bottom, the small ones will move faster, and the intermediary ones will be kind of in the middle. And you can actually do different kinds of calculations, which we do in lab, and calculate the RF, which is the retention factor, which is basically how far each individual pigment traveled versus how far the solvent traveled. So if this is your original line and we measure in centimeters, our new position, we see this one is 2.1 centimeters and this one is 2.8 centimeters. We can make a nice little ratio right here and say, all right, this has a retention factor of 0.75. And you can do this for a variety of different pigments as you go through. And you can see what are the biggest molecules and smallest molecules. I really like using like a brown or a purple or like a black ink, because then you can see all the different shades of all the different colors. And then you can also see the difference between Sharpies and Expo markers and your Crayola markers and see what dissolves in what. Okay, and should be no surprise, your Crayola markers are going to obviously dissolve in your soluble water molecules because we don't want kids to eat them. That would be very, very bad. All right, that is our like dissolves like.